So let's learn a little bit about the motivation for wanting to do CDR so desperately. Obviously, we have accumulated a lot of CO2 since Industrial Revolution. We already know from other podcasts that the warming is linearly proportional to the cumulative carbon. So anywhere you add another ton of CO2, it's going to cause additional warming, which means any ton of CO2 that you draw down is going to reduce that much warming from happening. So that's the main motivation. Plus, we are not really slowing down. The emissions continue to accelerate despite all the negotiations for 25 years. So everybody is trying to reduce emissions, but it's obvious that if we really want to keep global warming to low levels, then we need CDR as part of the portfolio of solutions other than decarbonizing the system, right? So anthropogenic CO2 and the motivation for CDR research and development come from that basic background. As of 2023, human activity adds approximately 35 gigatons of CO2 to Earth's atmosphere yearly from fossil fuel sources. If you make it CO2 equivalent, which means you add non-CO2 greenhouse gases to the total emissions, which is what we must do, then we are in the range of 40 to 50 gigatons CO2 per year, CO2 equivalent per year, sorry. So this is something to keep in mind. Roughly half of this added CO2 is absorbed into the oceans and terrestrial biomass, and the atmosphere accumulates a lot, which determines the global warming most directly, in addition to acidification and so on. Limiting the total warming from anthropogenic CO2 to 1.5 degrees C or 2 degrees C above pre-industrial times would involve removing multiple gigatons of CO2 per year of CDR later in this century, according to scenarios studied by the IPCC and others. Independent of such scenarios, estimates of climate sensitivity suggest that to limit warming to 1.5 degrees C, much or all of the net atmospheric CO2 increase beyond current levels would need to be offset by CDR. Okay, so gives you a ballpark number of how quickly we need to scale up. Even with a higher bound on atmospheric CO2 and significant emissions reductions, CDR at the scale of multiple gigatons of CO2 per year may be desired to offset continuing emissions. So you want to reduce emissions, but to the extent that we will continue for a while, we need CDR to scale up proportionately. So here is the standard canonical Keeling curve. It started, the time series started in the 1950s when Charles David Keeling was a graduate student at the Scripps Institute of Oceanography. So this is the CO2 fraction in dry air ppm, and these are the years going up to about 2024 when this, mid 2023. Sorry about that. And we know that there is a seasonal cycle, but the trend is that we continue to increase and even accelerate, which is bad news. With that background, I'm going to just straight ahead to some of the summaries of cyclic versus once through CDR systems. So carbon capture and removal, carbon dioxide removal, can be cyclical, which means you have some material that absorbs CO2 as the air is flowing through, and that material gets saturated, so you have to suddenly I got a frog in my throat. Desorb that CO2 so you can use that material again, or you have once through systems for CDR, which we'll look at. So CDR systems can be conceptually divided into two basic principles. Cyclic CDR systems, such as the chemical DAC, direct air capture, use a single batch of material to capture CO2 over and over again in a cyclical process. After material captures some CO2, the CO2 is extracted, typically using heat, which means energy. The CO2 is separated into relatively pure stream suitable for storage, so it can be geologic sequestration, mineralization, utilization, whatever, and the material is reused in the next cycle for absorbing more CO2. The primary input, aside from air for cyclic systems, is energy, although some cyclic systems also require substantial amounts of water, And in application, materials degrade and must be replaced over time. So how many cycles you can have of reuse matters a lot. For cyclic CDR systems, the second law of thermodynamics gives a lower bound on required energy. So you cannot reduce the energy requirements beyond a certain lower bound. So you want to do research to see if we can push it down and push the efficiency of the adsorption and the recycling or life cycles, lifespan of these materials that do the adsorption. So here we are, some material that is able to bound CO2 with it. So you have atmospheric CO2 flowing through the binding, flowing through the system, the material, and the binding process happens. So you reduce the CO2 in the atmosphere. So you release some air after the flow through. Obviously, you are emitting some air out on the other end, which has got reduced CO2. So the CO2 that's captured is bound with the material that's being used for absorption, and then you have to separate the CO2 from the material using energy, heat, etc., to release pure CO2 that's capturable, obviously, and then you use it or store it and so on. So there is energy input involved here and some energy input involved here, often depending on what exact cyclical process is being used. In the once-through CDR systems, such as enhanced weathering, where you grind up rocks and spread them on land, and it's done. You cannot recapture that material and recycle it. Also, ocean alkalinity enhancement we have discussed elsewhere, and these use materials that are out of equilibrium with the atmosphere, such as alkaline materials extracted from the earth or certain kinds of industrial byproducts. After being processed, for example, by grinding into a fine powder, this material is distributed broadly and allowed to react with atmospheric CO2 to bind the carbon. The reaction products are often left in place and or dispersed into the environment with potentially significant negative or positive environmental consequences. Obviously, you want to reduce negative consequences. In more controlled situations, the products may be disposed of or used in industrial processes, such as in construction materials. The essential difference between these two types of systems is that the thermodynamic bound on minimum energy needs applies directly to all cyclic systems, but not to once-through systems. So you can keep on grinding up rocks and putting them on fields or forests or whatever, agricultural lands, etc., if they enhance soil properties for crop yields increasing and so on. And obviously you want to think about energy needed, but you can think of doing it with renewable energies so that you are not using energy to release CO2 to then capture CO2 and look for small additional sequestrations, etc. As we'll see later, monitoring and reporting, we already mentioned this in the executive summary. Making sure that additional CO2 is being sequestered actually by these once-through systems like ocean alkalinity and enhanced weathering is not very easy, as opposed to the cyclical systems where you know how much CO2 you are capturing, right? So this is how it would work. You can start anywhere. Extracted raw material, which is alkaline, energy input is needed to grind them and process the material. You want to increase the surface area to volume ratio so that the exposed area can quickly weather, because weathering is a geologic time process anyways, but you are trying to enhance the rates to make them work right now at a very fast rate. So the binding reaction happens, and material with bound CO2 and carbon output waste material dispersed, buried, or used, and you have atmospheric CO2 that is reduced in the air that is being released after the flow through of the high CO2 ambient air has done its job of enhanced weathering or going into the ocean with the enhanced alkalinity approaches. Okay, so we have discussed this already, so I'm not being too detailed about this. So CO2 capture methodologies can be roughly separated into cyclic and once-through systems. Key difference, of course, is that there is energetic constraints from thermodynamic thermodynamics that provide a clear lower bound on the energy needed for cyclic processes, while for many ones through CDR approaches, such as enhanced rock weathering or ocean alkalinity enhancement, some of this energy has been supplied over millennia by natural processes. So if you just grind up the material and put it or enhance the alkalinity, then nature can do rest of the work. We characterize a cyclic carbon capture process as one in which materials involved in capture processes are reused. So I won't read all this again, but the outputs of once through processes include modified version of the input material that cannot easily be reused to capture more carbon. That's why you call them once through, right? So cyclic and once through capture systems generally have different types of physical constraints as well as different environmental impacts. These also have different measurements, reporting and verification concerns, and technical challenges, which we will address. We read a little bit in the executive summary. We'll come back to this later on. So here is a figure, just a schematic showing how the main approaches that have been proposed for atmospheric CDR work. So DAC, direct air capture, enhanced rock weathering, ecosystem-based CDR, so biological processes, bioenergy with carbon capture and storage. We already mentioned how these can compete with food and water, and ocean alkalinity enhancement. Again, just a kind of schematic. I won't go into these because I have detailed podcasts on each of these elsewhere. We are just adding some physical mechanistic understanding and thermodynamics of these processes in this set of podcasts, right? So what are the physical limits on capture of atmospheric CO2 then? Energy constraints from thermodynamics of the processes involved, where you are absorbing and desorbing CO2 in cyclical processes, of course, is driven by reaction kinetics and thermodynamics. So energy constraints on cyclic CDR systems, then the second law of thermodynamics gives us a well understood absolute lower bound on the energy cost of CO2 capture for any cyclic CDR process. Energy needed will be greater than equal to 120 kilowatt hours per ton of CO2. Okay, there are technical details provided in the appendices of the report that I'm not going to read. This lower bound describes the amount of energy needed regardless of its source. Could be renewable or fossil fuel. Obviously, you want renewable to reduce emissions. If a system uses thermal energy as its input, which is from fossil fuel or coal, only a fraction of the input energy can be applied toward this bound. This absolute lower bound gives a useful metric for evaluating different approaches to carbon capture. Most existing and proposed methods for chemical DAC require energy input of at least 3 to 10 times this lower bound, even when considering only the useful fraction of energy from thermal sources. Capturing CO2 at the rate of 1 gigaton per year using energy at 3 to 10 times the thermodynamic lower bound would require generating new carbon-free power at a level of 1 to 4% of the 2021 global electric power generation. So this is a nice little back of the envelope calculation that once you know the lower bound of the energy needed to do cyclic atmospheric CO2 drawdown, CDR, then you know what the level of drawdown is needed. So for each gigaton of drawdown, you will need a certain amount of energy. So now you know how much renewable energy is needed to grow in the coming years. So the second law of thermodynamics imposes a fundamental lower limit on the energy needed by any cyclic direct air capture processes. The mixing of carbon dioxide molecules with the dominant nitrogen and oxygen molecules in the atmosphere involves a high degree of disorder or entropy. Removing this disorder by sorting the molecules, i.e. separating out the CO2, requires energy because the entropy must be dumped back into the atmosphere through the transfer of thermal energy. Words, but basically you know that CO2 is a trace gas, 0.04%, so you have to flow through a lot of air to capture this little amount, which is what we mean when we say entropy and so on. Quantitatively, the thermodynamic lower bound states that the energy cost of separating 1 ton of CO2 from the atmosphere is at least 120 kilowatt hours, You can look at Appendix C for the details. This means that the minimum energy cost of removing 1 gigaton of CO2 per year would be equivalent to the full output of 14 nuclear power plants generating a continuous power output of 1 gigawatt equivalent each year. Or sorry, 1 gigawatt equivalent each. So you have 14 nuclear power plants doing that, and they are comparable to yearly energy use in mining Bitcoin circa 2023. So we are doing AI, which takes a lot of energy, Bitcoins, which take a lot of energy, and then we want to do CDR, which needs a lot of energy. So we can compare. Is CDR much more useful than Bitcoin and AI? Well, this is the value system we have to work through. At a more realistic rate of energy use of 3 to 10 times the thermodynamic minimum, the steady state power requirement for each gigaton of CO2 per year of CDR would be 40 to 140 gigawatt equivalent. This is 1 to 4% of the current global rate of electric power generation. This lower bound on energy requirements is very familiar to scientists and engineers working on carbon capture systems, but must be considered in any discussion of scaling and large-scale implementation of carbon capture systems. Okay, so let me see how long am I here. We can flip, yeah, already 16 minutes, so let's stop this here, but let me check something before I close it. So I'm going to pause it and come back.